Alrighty, so in this video I'm going to review the June 2011 Unit 2 paper. So a boy throws a ball vertically upwards and then lets it fall to the ground, and we've got a displacement versus time graph. So let's just talk through what we can see here. So this is the height from which it was originally thrown, so it's above the ground, it reaches a maximum height, then comes back down again all the way to the ground and then bounces. That's what we can see there. So state which feature of this graph represents velocity. It's the gradient of the graph, and then looks how we're linking that in, and then we're going to sketch what the velocity versus time graph looks like. Okay, so we've got the gradient is the velocity, the gradient is the velocity, and we want to draw what the velocity time graph looks like between the two. So we've been given no indication that there is any air resistance, so essentially the acceleration should be constant and would be minus g. So we're going to have a straight line graph. When it reaches the top, it's going to be going at 0 because it becomes stationary at the top, and then it's going to come back down, and because it falls further, it's going to be sort of somewhere down here. So this line might not turn out too straight because it's difficult on my screen, but let's have a go. Okay, so this is meant to show a straight line graph going through 0 at t1 and then ending up at a slightly larger speed compared to this one over here. Okay, so that's the graph. Let's continue on. So we've got sort of a snapshot of what the ball looks like as it's bouncing, and you can see it's been deformed by bouncing as the kinetic energy of the ball is transferred to deform the ball, so storing it in the form of kind of elastic potential energy, if you like. Explain how Newton's third law of motion applies to figure 2. So the ball is colliding with the ground and the ball is being brought to rest. So therefore a upward force is acting on the ball. So therefore, using Newton's third law, an equal and opposite force is acting on the floor there. So that's the reaction to it. So let's get that down. Okay, so that's what we've got there. So when it's hitting the ground, the velocity is being decreased, which means there's an upward force acting on the ball, essentially against its motion, and that's coming from the ground. So using Newton's third law, there must be an equal and opposite force acting downward from the ball on the ground. That's the action and reaction. Explain why there is a resultant upward force on the ball in figure 2. So essentially, if we look at the forces acting on the ball, there is a downwards weight force of it, and then if it's slowing down, there must be an upward force from the ground that is bigger than the weight force. That's what would allow it to slow down or accelerate upwards, if you like. Okay, so that's what we've got there. So to slow down, there needs to be a resultant force upwards, so that the force from the ground must be greater than that of the weight force to allow that to happen. So that finishes question 1. Let's move on quickly. Okay, so a student measures the acceleration due to gravity using the apparatus shown in the diagram. So we've got a light gate, a card, and that's all connected up to a computer. So we know the length of the card, and it's dropped from 0.5 meters above the light gate, and the computer calculates velocity using the time taken for the card to pass through the light gate. Seems fair enough. Okay, the computer calculated a value of 3.1 meters per second as it traveled through the light gate. Calculate a value for the acceleration due to gravity from these data. So it's released from a height of 0.5, and we've got its final velocity, and we know its initial velocity. So let's get our SUVAT parts down. That's what we've got there. So it's going to fall 0.5 meters, so the displacement will be minus 0.5. The initial velocity is 0 because we're dropping it. We've got its final velocity and we want the acceleration. So we need the equation that doesn't have t in it. So we're going to use v squared is equal to u squared plus 2as. U is 0, so we can get rid of that. So we want a, so that's going to be v squared over 2s. So that's 3.10 squared over 2 times minus 0.5. So that's effectively minus 1. And that gives an acceleration of 9.61 or 9.6 meters per second squared to two significant figures. Or it's just so they would state the acceleration due to gravity as 9.6 because we know it's the gravity acts downwards anyway, so that's the value of it there. Okay, so let's crack on. The student doubles the mass of the card and finds a value for g that is similar to the original value. Use the relationship between weight, mass and g to explain this result. So first of all, the acceleration is the resultant force divided by the mass, and the force is the weight force, which is mg. So then in theory it shouldn't matter what the mass is, you should get an acceleration due to g, because the masses always cancel out. So let's put down some words to explain what we're showing. So that's what we've got there. So that's how we get the acceleration. Masses cancel out, so mass has no effect on the acceleration. All right, so let's move on to the next part. State and explain one reason why the card would give more reliable results than a table tennis ball for the same experiment. So a table tennis ball will have a much larger surface area, so therefore it's going to be affected more by air resistance. So you'd find your value of g was smaller than before. So let's put that down. All right, so let's just review we've got there. So the key difference is the surface area presented to the air. So the card, if we're dropping it like end down, has a really small area presented to the air particles. A table tennis ball has a much larger area, so you'd expect to get a smaller value of g with the table tennis ball because its resultant force is smaller due to air resistance. Okay, so that concludes question 2. All right, so we've got some more motion type stuff going on. So we've got a roller coaster when it's being accelerated by a cable. So we've got, goes from 0 to 58 in 3.5 seconds. We've got its mass, calculate its acceleration. So again, we're going to use some suvat here. So here's what we've got. We don't have displacement, so we want an equation without displacement. So we're going to use the only equation in which that's true, equals u plus at. U is 0, so we can get rid of that. So acceleration is going to be v over t, that's 58, divided by 3.5, and if we do that, we end up with 17 meters per second to 2SF there. Okay, so fairly straightforward. Calculate the average tension in the cable, stating appropriate unit. So we can use Newton's second law here. F equals ma. So we're going to use our unrounded value of a, so it's like 16.57, yada, 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 times by the mass, which was 5,800, giving us a resultant force of around 96,000 odd, so 9.6 times 10 to the 4 newtons there. And yeah, unit of force is newtons, so that would be your appropriate unit. All right, this is carry. Okay, so it wants to calculate the distance the train moves while accelerating from rest. So let's get our suvat out again. So we actually know all components of it. I'm going to pick the one without acceleration because it means we don't have to use like unrounded values or whatever from before. So the equation without acceleration is this one. U plus v over 2 times by t. U is 0, so let's get rid of that straight away. So S is going to be 58 divided by 2 times by 3.5, and when we do that, it's like 101.5, so 1.0 times 10 to the 2 would be appropriate enough to 2 sig figs there. The efficiency of the roller coaster acceleration system is 20%. Calculate the average power input to the system during the acceleration. So let's calculate the change in kinetic energy. Because we know the time, we can then convert that to power. So this would be the useful energy. So that's half m v squared. So half times 5800 times by 58 squared, which gives us a value of. So that gives us like 9.75 blah 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 times 10 to the 6. Power is going to be the rate of change of energy, so that's the only type of energy that's changing. So that's our answer divided by 3.5. Divided by 3.5 gives us 2.7787 times 10 to the 6. That's the useful. So what we need to do, that's the use represent the useful. So we need to multiply by 5 to find out what 100% is. 5 gives us 13.9 million. So that's basically 14 megawatts to 2 significant figures there. Okay, so let's just write on there what I'm doing. So I'm timesing it by 5 to go from there to there because it's 20%. Okay, so after reaching its top speed, the driving force is removed and the roller coaster train begins to ascend a steep track. By considering energy transfers, calculate the maximum height it can reach if there's no friction. So what we're going to do is all of its kinetic energy is going to be transferred into GPE. So the final height is going to be the kinetic energy divided by the mass times gravity. So let's get that up. So a kinetic energy was at 9.7 odd million divided by 5,800 divided by 9.81 gives us 171 odds. So that's going to be 1.7 times 10 to the 2 meters there to 2 significant figures. All right, so that finishes question 3. Okay, so we've got horses were once used to power machinery in factories, mills and mines. We've got 2 horses attached to a beam to turn a wheel. So we're going to be dealing with moments. Anytime we've got any turning, that's going to be about moments. Each horse exerts a force of 810 newtons and the beam length is 7.3. Define the moment of a couple. So the moment of each of them so one horse is going to have 810 times by 7.3 over 2, because that's the force times perpendicular distance. Because it's a couple, there are 2 of those. So we're going to do 810 times by 7.3 over 2 times 2. So it's just going to be 810 times 7.3, or force times the distance between the forces. So let's put that into text. Okay, so remembering the key features of our definitions of moments, that it's perpendicular distance between lines of action, and for a couple it's the distance between the 2 forces that make up the couple. Okay, so the next question wants us to calculate the moment of the couple exerted by the horses, stating an appropriate unit. So the moment of a couple is the force times the distance between them. So it's just 810 times by 7.3, which gives us a value of 5913, or 5.9 times 10. So the 3 Newton meters there. That's your final answer. We want to do the two horses separately to show that that's true. So the moment of just one horse is force times the distance to the center of rotation, so 810 times by 7.3 over 2. So the total moment is going to be double that, because they're both acting in the same direction, so you can see that it's 810 times, say, 7.3, which is exactly what we had there. So you can see either doing it separately or as a couple combined, we end up with the same answer. That should be fine. Okay, so let's move on. Okay, so the horses move at a constant speed of 0.91. Calculate the combined power output of the two horses. So to get the power, we're going to do power is force times by the velocity. So it's going to be 2 times 810 times by 0.91. The 2 is because there are two horses. So we end up with 1474, which is basically 1.5 times 10 to the 3 watts to two significant figures, which is appropriate because this value here is quoted to two significant figures. Okay, so during the Industrial Revolution, the 19th century, James Watt became well known for developing and improving steam engines to replace horses, hence why he's got the name, or his name is the unit of power, and he also defined something called horsepower by studying a system. Suggest reasons why Watt used horsepower as a unit of power. It's just going to be allow people who are buying his product to compare what it can do to what they can currently do, because everyone was using horses, so he wanted to essentially show them how much better his steam engines were than horses. So if it has 100 horsepower, it's as good as 100 horses, maybe for the same price as one horse, so it makes it understandable for people. Alrighty, so that's what we've got there. Essentially, a lot of the units that are not fundamental units have been created as a way to make things more easily translatable. So things like, I don't know, the electron volt, it makes it more helpful when you're looking at particle physics. The unit of pascals just simplifies looking at pressure. So that's where these things come from, to make things easier to understand. Okay, so let's carry on. Okay, so the speed of light is given by the wave equation with the speed of light in it instead of velocity. State how each of these quantities will change, if at all, when light travels from air into glass. So glass has a higher optical density than air, so speed is going to decrease. Nothing can change frequency because nothing can change a photon's energy during its travel, so the frequency stays the same, and so speed and wavelength are directly proportional to each other. So if speed decreases, wavelength will decrease too. So let's get that down. Alright, so we've got that. So if we look at a side view of an optical fibre, this question looks very similar to one we had a couple of years ago. We've got two light rays going in, and we've got a core, our cladding, the key parts of an optical fibre. So ray A enters the end of the optical fibre and then undergoes total internal reflection. Complete the path of this ray along the fibre. So if it undergoes reflection, that's going to essentially just be reflected off of the boundary. So it's going to go, well, it's a bit wonky. Something like that, where this angle in here and this angle in here should be the same as each other. So angle of incidence equals the angle of reflection, effectively. So that's what you'd be looking for there. So the speed of light in the core, it has this value. Show that the refractive index of the core is 1.47. So to calculate refractive index, it's the speed of light in a vacuum divided by the speed of light in the substance. So it will be 3 times 10 to the 8 divided by 2.04 times 10 to the 8, which gives a value of 1.4. We're not 7 yet. We've got a 4 first. So we've got 1.4706, which is approximately 1.47 there. So we can see that that's worked out. Show that the critical angle at the boundary between the core and the cladding is about 80 degrees. So when we have critical angle, that's just equal to this because the angle of refraction is 90 degrees. So we can get the critical angle is going to be the inverse sine of n2 over n1, so it's going from the core into the cladding, so n2 is going to be the cladding, and the core is going to be 1.4706, yeah. So when we do that and calculate the answer, we get 80.401, which is roughly 80 degrees here. So you'll see that for these show that questions, I always give a few more decimal places to show I've actually calculated it, and then show, say, you know, that's roughly what we were looking for. Okay, so let's carry on. So we've got ray B enters the end of the fibre and refracts along the core cladding boundary. Calculate its original angle of incidence when it entered the fibre. So if it goes along the boundary, we know its angle of incidence with the core cladding boundary must be the critical angle. So if I draw the normal, so essentially the ray, it must be coming at this at 80.4. So then if we complete the right angle, so we know its angle of refraction is going to be 90 minus 80.4, which is going to be 9.6 degrees. That's the angle of refraction after it's crossed the boundary into the optical fibre. So now we can apply Snell's law, because we want the angle of original angle of incidence, R. So the angle of incidence is going to be the inverse sine of n2 over n1 multiplied by sine of R. When we put these values into here, so we put the air in as n1, the core is in as n2, and then our 9.6 as sine R, we end up with 14.194, so that's 14 degrees there as your final answer. Okay, so we've got a pulse being sent through an optical fibre, and it comes, you can see it's coming out very differently, and it wants us to explain why the pulse has a lower amplitude and is longer than it is at x. So if a pulse gets broader, that means pulse broadening has happened, which is caused by multi-path dispersion, so the waves taking different paths from x to y. The decrease in amplitude will be due to energy being absorbed as it passes along the optical fibre. So let's put those two down. Alright, so that's what we've got there. So the 2 points for the 2 marks. Amplitude decreases as energy is absorbed. Let's fix my very poor writing. As energy absorbed as the light passes through the optical fibre, pulse broadening occurs as light can take different length pathways to travel from X to Y, which is a process called multi-path dispersion there. Okay, so that finishes that question. Let's carry on. Okay, so this question wants us to plot some data on a graph. I'm honestly not going to waste time plotting data on a graph. Hopefully you should be able to scale and plot data on a graph. It's not really a productive use of time here. And to find the Young modulus, what we need to do is find the gradient of the straight line section of the graph. So when you plot this data, you end up with a straight line section. So you should end up with something, if you do this correctly, stress versus strain, you end up with a graph that looks something like this. So what you need to do is find the gradient of the straight line section. That would be your Young modulus there. So let's write that down. Find the gradient of the straight line section. All right, so that's that. I'm not going to do that. It's not really a good use of time. So let's carry on. So the next one, a 3 meter length of steel rod is going to be used in the construction of the bridge. The force applied will be 10 kilonewtons, and its extension can only be 1 millimeter. Calculate the minimum cross-sectional area for the rod, given that we've got Young modulus. So Young modulus is calculated by doing stress over strain, so that's force divided by area over change in length for original length. So we want to get the area, so that's going to be FL over E delta L. So that's going to be 10,000, that's the force in newtons, times by 3, that's the original length, over 1.9 times 10 to the 11, times by 1 times 10 to the minus 3, that's your extension. We do all of that, we will get a value of, that's like 1.5789 times 10 to the minus 4, so it would be to an appropriate number of significant figures, 1.6 times 10 to the minus 4 meters squared would be your minimum area, and then any area bigger than that would be fine. Okay, so that finishes that question. So we're going to have a longer answer question here because we haven't had one yet, and indeed we do. So we're going to use a double slit to measure the wavelength from a laser. So we know what the slit separation of the laser is, describe the measurements that need to be taken, and explain how they can be used to find the wavelength, discuss any necessary safety precautions and how you can improve accuracy. So let's first look at our double slit equation so we can understand what's going on. So the fringe spacing is lambda d over s, and we know that wavelength, we're going to use the same laser, so that's going to stay the same. S is going to stay the same. So what we want to do is vary d and then measure what the spacing between the fringes is. That's going to be the general method we're going to use. So let's explain how we're going to set up the equipment. Okay, so what we're going to do is we're going to set it up so the slit is 1 meter from the screen and the laser is angled normally to the slit, and we can check that using a set square. So once we've done that, what we're going to do is take our first measurement, and to improve accuracy we're going to measure multiple fringe spacings and divide by the number of spacings. Okay, so that's what we've got, and we've got our strategy to improve accuracy already. So then we're going to need to change the screen distance and repeat this process. All right, so this is the process we're going to carry. So we're taking one full set of readings. So now what we're going to need to do is repeat that experiment so we can get average fringe spacing for each distance, and then we can plot our graph. Okay. All right, so that's what we've got there. we've got average fringe spacing, we've got distance, so we can plot those two things on the graph. So then finally, how are we going to get the wavelength from that? Well, we're going to use the gradient of the graph. Okay, so that's our final stage, multiplying the gradient by the slip separation to give the wavelength, because we can see from this equation the gradient would be lambda over s. So let's check the bullet points and see if we've done everything. We've described the measurements and how we've described how they're going to be used. We haven't yet talked about some safety, and I think there's another strategy we can talk about to improve accuracy. So let's finish off by talking about that. So safety, we need to make sure the laser's pointed away from people. If we've got them, wear some laser safety goggles, and if you want to really be safe, put up some signs to make sure everyone's aware there are lasers going on. And another strategy to improve accuracy is we're going to want to turn off any lights in the room and black out any windows, because that makes the fringes clear and fringe spacings easier to measure. Okay. All right, so we've got those 2 points now, and that would finish off our answer nicely. Just a quick little thing, I've mentioned this in a few other videos, but just in case you haven't watched those, make sure you don't write outside this box in the real exam, because nothing in this section will get marked, because it's only what's inside the box that gets scanned in, so be careful with that. Okay, so that's that question. Let's finish off the paper. Okay, so Thomas Young used the candlelight to observe the interference pattern from two narrow slits, acting as coherent sources. What is meant by coherent sources? This seems to come up on pretty much every exam. It means your sources of light, or the light from both slits, has a fixed phase difference. So let's write that down. All right, so I'm not sure why the examiners thought we needed so much space. That's pretty straightforward. But anyway, so sketch and label on the diagram the arrangement Young would have to use to obtain his interference pattern. So to get the candlelight to be coherent, you need to use a single slit first. Let's draw one of those. So it needs to go through a single slit, and then that is then shown through a double slit, because what it allows to do is light spreads out from this one slit, which gives you your coherent sources of light. So your light's coming in here, is diffracted outwards, so it essentially goes over the two slits, and then you get your interference pattern from that. So let's just label our diagram. That's we've got, so it goes through the single slit first, then the double slit. All right, so two differences in the appearance of the pattern obtained with a laser and that produced by a white light source. So with a laser, that's going to be monochromatic, so all the fringes are going to be one color. With a white light source, the central fringe will be white, and then the outer ones will go from violet through the full spectrum to red. You'd expect the fringes to be less intense with a candle, because it's not dispensing as much energy per second. So let's get a few of those down. Okay, so that's what we've got there. You could also talk about the fringe spacing, because with white light you'd have wider fringes or smaller spacing than you do with the laser. So that could be another one, but those are the two I would go with here. So contrary to up here where they gave us too much space, didn't get enough here, but never mind. So explain how the wave theory of light accounts for the areas on the screen where intensity is a minimum. So what's happened there is the two sources of light have met out in antiphase, or 180 degrees phase difference, and caused destructive superposition to occur. So that's what we've got there, and make sure it's not just that they're out of phase, that they're 180 degrees out of phase or in antiphase. Okay, so that completes this paper. I hope you found that useful to help you answer the questions. If there's anything that's not clear, please do let me know. And again, if you have any questions, please do comment and ask me. Thank you for taking the time to watch. Do make sure you check out my playlists on Unit 1, 4 and 5 as well to get help with those. But thank you for taking the time to watch this video.